Okay, so in this lecture we are going to talk about the very important topic of simulating data. Now, why would you want to simulate data? Well, the main purpose of simulation is going to be to understand the statistical power properties of our experiment design. And why would we want to do that? Well, first of all, we will typically want to do a power analysis before we run the experiment in order to decide on the sample size that we will need to have adequate power. So if you remember, we had done in a previous lecture, so lecture 3, we had talked about statistical power, which is the probability of your correctly rejecting the null hypothesis. That means when the null hypothesis is actually false, what's the with some particular value, what is the probability that you will reject that null hypothesis, right? So that power needs to be high, because if power is high, then type 2 error is low, and we want to keep type 2 error low. Type 2 error, if you remember, is the probability of failing to reject the null when the null is actually false with some particular value. Okay, so you want to keep this type 2 error low. This 1 minus beta is power, and we want to keep that high, and so we want to set up a design such that we have as high a power as possible. So for that we will need simulation, because we will have very complicated experiment designs with repeated measurements, and simple power.t.test functions can give you an approximation, as I will show you, but they can't really give you reliable estimates of power in your particular design. Okay, another reason why you want to simulate data once you've done an experiment, the experiment is done, you may still want to study the power properties of your experimental data for a future experiment, and in doing so understand whether you are in a type M error situation. So suppose you do an experiment and you get a significant result. That sounds exciting, but what would happen if you ran that experiment many times with some reasonable value for the effect size? If you're unlikely to detect that effect again, then that's a strong indication that you have an accidental type M error situation. Okay, so these are ways to think about your result, going beyond the simple p-value diagnostic. So to understand the power properties is crucial when you do an experiment. Another reason you want to do simulation is to understand which parameters you can recover in principle, under hypothetical repeated sampling. So you repeatedly generate simulated data, and you draw the distribution of each of the parameters that you estimate in each time you fit the model. I will just show you an example, of course, and this will help you understand whether your model makes sense at all or not, right? Whether it can recover the parameters or not. So I will show an example. So we will start by looking at a very simple scenario between subjects design. The purpose of this simple scenario is to just get you into the flow of doing simulations. In practice, I never use between subjects simulations, because I never have between subjects designs, or almost never. I usually have within subjects designs. So once I prepare you with a between subjects design simulation, then I will switch to the within subjects design and show you how you can generate data that we would typically analyze using a linear mixed model. Okay, so let's start with a simple case. So suppose we have reading time data in milliseconds from 10 subjects, and these subjects see subject relative clauses. Okay, and we have a different set of 10 subjects who see object relative clauses, right? So each subject has seen either a subject relative clause or an object relative clause, but not both, and we have a total of 20 subjects, right? So we're going to assume that standard deviation, so the residual standard deviation is 300, the true subject relative reading time is 700, and the true object relative reading time is 750. Okay, so the true difference between the subject and object relatives is 50 milliseconds, right? So how to simulate this kind of data, right? So we're going to generate hypothetical data under these assumptions of each of these parameter values. Okay, residual standard deviation 300, subject relative reading time 700, object relative reading time 750. Okay, so what we're going to do is we take 10 samples from the subject relative normal distribution. So we assume that the normal distribution is generating the data. We could have assumed something else, like log normal or gamma or something, but in this course we just keep it simple. And for the object relative, we simulate 10 data points coming from normal distribution with this mean and standard deviation. And then we just create a data frame with the appropriate subject ID. Okay, so how do we do that? So let's do this. For subject relatives, I generate 10 data points from this distribution. For object relatives, 10 data points from this distribution. And now I create a vector going from 1 to 20. And I create a column called cond for condition, which has 10 instances of subject relatives and 10 of object relatives. So that's what this command does. And now I just created a simulated data frame called simdat. That is, a data frame has a column called subject, and this sub is a vector going from 1 to 20, has the condition column which has 10 instances of subject relative, 10 instances of object relatives, and the concatenated vector of SROR reading times that we just generated here. So this is all simulated data now. We just generated our first simulated data set. Okay. So now the interesting question is, how can I generalize this? How can I repeatedly generate such data, right? So I could do this again and again, what I've just done here, but there's a better way to do this, and the better way is to write a function. So we're going to write a function that for a particular sample size in each condition, that's what that n refers to. I want to remind you of homework 1 there, right? And the mean for the first condition is this, the mean for the second condition is this one here, the standard deviation is here. So these are all the parameters that go in this function, and this will generate, this function called between subject simulate data is going to generate now n data points for subject relatives, n data points for object relatives, create a vector going from 1 to 2 times n, right? So if n is 10, then it will be 20, and then create the condition factor with n replications of SR and n replications of OR. That's what this command does, and wrap it inside factors so that these are considered to be factors and not strings. Okay. And now we just create a data frame with the subject column, condition column, and the reading times. Okay, so now, and then it prints out the data frame. So what this function does is, you can just take the default values if you want to generate 10 data points with the given parameter values that are the default values here. You can generate data repeatedly now. So here, what I'm going to do, what this for loop will do is 100 times it will generate a completely new fake data set, simulated data set, using the parameter settings that I gave it. Okay. So now, why would I want to generate repeated data like this? The reason is that I can use this now to do power analysis and to check if the model recovers the parameters correctly. This is what I mentioned earlier. Okay, so let's take a look at how this works. First of all, I want to remind you of the power.t.test function that we used, I think, in homework 1. So imagine that the difference between the two means is 50 milliseconds. We have a sample size of 10 in each condition and a standard deviation of 300. It's a 2-sample experiment and it's a 2-sided t-test. Okay, so we're going to do the t-test and compute power here, and when I compute power to 3 decimal places, I get a power of 0.064. Okay, I'm going to now do the same power analysis. I'm going to compute power using simulation, by simulating data repeatedly. Okay, and you will see that I'll get a very similar number. Okay, so let's say I simulate 100,000 times the following. Okay, I'm going to run 100,000 simulations in this for loop. Each time I'm going to generate a simulated data set using my built-in function, not my built-in function, but using my handcrafted function. And once I have the simulated data, and you remember what it looks like, something like this. So I'm going to have RT as a function of condition in a between subjects design. So I'm going to say t.test RT as a function of condition, paired equal to false. Why? Because it's a between subjects design. give the data frame as an input to the t.test function, and extract the t value, right? And save the t value in a vector that we create before we start the simulation. We create this vector observed t values with 100,000 empty cells, and each time this for loop runs 100,000 times, the ith cell of this vector observed t will be saved in this vector. And so we can use that vector, this observed t vector, we can compute the absolute value of this thing and then find out what proportion of these observed t values, the absolute observed t values, exceed the critical t value, the absolute critical t value, right? And that number, the proportion of cases of the observed t value that exceeds the critical t value, of course the absolute values, will be the statistical power, right? So in this case, power is 0.06, which is pretty much the same number that we got here. Okay, so what I'm showing you here is that for these simple designs, you can either use the analytical approach of the power.t.test function, or you can just use simulation. You know, you'll get pretty similar conclusions. Okay, so next what we're going to do is we're going to learn how to compute power using simulation in between subjects designs, but this time we're going to use the linear modeling framework. We're not going to use the t-test, right? So in this case I was using the t-test, but we're going to use this time the linear model. Okay, alright, so then after that, once we've done that, we'll learn how to compute power for within subjects design using t-test and Elmer. Okay, so first of all, the default contrast coding that I'm using here is of course the treatment contrast, because I didn't mess around with the contrast coding yet for SR and OR, right? And OR is coded as 0 and SR is 1 because of the alphabetical ordering here. O comes before S, that's why. That's the only reason. Okay, anyway, so now we do our usual thing, which is to recode our contrast as some contrast. So I've just redefined the contrast coding as some contrast, and now I've got OR is +1, SR is -1. The method I prefer, of course, is this one, where I use the if-else function to code the OR is +1 and the other condition is -1. Notice that I'm not using any NA or anything like that here for any other situation, right? So there are only two conditions. So I just, because I have only two conditions, I know that. So for one I have +1, for the other one I have -1, and so I create a new vector called RC type, which is going to be my predictor now. Okay, so I mean I could do that, but I'm going to use cond just to be consistent with the story right now. Okay, so now in this two sample t-test and ANOVA, and I showed you earlier that the two sample t-test, ANOVA, that is the likelihood ratio test, and the linear model are all exactly the same thing. Okay, so let me just remind you of this thing. So when I do this t-test with RT as a function of condition in a between subjects design, and I extract the t statistic, I get -2.444. Okay, if I do a linear model on the same data and extract the ANOVA, I get an F score of 5.97. Now if you remember, F is equal to is the same thing as t squared, right? So if I take the square root of the F, I'm going to get the t value, which is exactly 2.444. Okay, so well, very close to 2.444. So, and similarly, like if I do the linear model and I look at the t value in the linear model, lo and behold, I again get the same t value, right? So the t-test, ANOVA, linear model, they're all the same thing basically, right? Not basically, they are the same thing. Alright, so now how to do simulation using the linear modeling framework. So we're going to write the linear model as follows. For every row I in the data frame that we have, the reading time called RT is going to be generated from a model where the contrast coding of the condition column in the ith row of the data frame is going to be coded +1 or -1. Okay, depending on whether we are looking at whether the row contains a subject relative or an object relative clause data point. Okay, so just to go back here, so whenever if the first row has SR, it'll be coded as -1. and if any further row has an OR, it will be coded as +1, right? That is what we are doing here, right? And we are going to assume that there's Gaussian noise on the residual noise is there. Okay, for every data point there will be some residual noise coming from this normal distribution with mean 0, standard deviation 300. Okay, so we've set up a linear model generative process now, where we say that every ith row of the data frame is generated from this model. Okay, so what that means is that we'll be computing this quantity with this coded as +1 or -1 depending on what's in the ith row of the data frame, and we'll have some random number, one random number that we'll have produced from this normal distribution in the ith row. Okay, so what we will have is for the first 10 rows of the data frame we have only subject relatives which are coded as -1, and for the second 10 rows we have object relatives which are coded as +1. Okay, so what the data frame looks like in matrix form is like this. Okay, what we have is 20 rows. Okay, and the intercept is always 725. Remember, I'm just using the multiplied by 1 here because in the design matrix the first column is always 1, right? That's why this one is there. And the second part here that you're seeing, this is the 25 millisecond effect in the +1 -1 coding. The effect size is going to be half that of the case when we have effect coding, right? With 0.5 ±0.5 coding, we would have had to write 50 here, not 25. Okay, so I hope you remember this discussion from the contrast coding lectures. So anyhow, the first 10 rows will have -1 because they are subject relatives. The second 10 rows will have +1 because they are object relatives, and then we'll have some Gaussian noise here. Every number will be different because it's generated from a different generated afresh from a normal distribution. Just one data point is generated, right? So one residual value is generated. So this is how. So if I compute each of these numbers, these 20 rows of values, I'm going to get some predicted data. Okay, so how do we proceed? Remember that like whenever we do such so whenever we have such data, we can, once we've generated the simulated data using this kind of a setup, what we can then do is that we can do a hypothesis test in the usual way, the way I have taught you in homework 4, I think, using the ANOVA function and so on. You could even look at the t-value, and look here, the t-value for my simulated data. This is with the simdat function. I had produced that data. You know, the simdat data I had produced, I get the same t-value here, and I get some p-value which you can extract from this command, right? So if you use summary, name of the model, $coefficients, and then the second row, fourth column, that gives you the p-value, right? Because this is the second row, this is the second row, and this is the fourth column, and here's the p-value, right? This is in scientific notation, that's why it looks so funny. It's 2.5 multiplied by 10 to the power of -2, right? And so that exactly corresponds to 0.02, right? Okay, so that's what this extracts for you. It extracts the p-value, and we're going to use that in a moment. Okay, all right. So alternatively, of course, you could do the likelihood ratio test and extract the p-value from that. It's going to be exactly the same number, right? Because these are identical tests. So you can decide whether you want to use the ANOVA or the t-test output, the linear modeling output, to extract the p-value. When you have unbalanced data, right, then you should always be using the ANOVA function and not using the t-value. You should not be using this t-value to decide on significance, you know, if you have missingness in the data. All right, so this is a more general approach. Okay, all right, that was just a side note. But now I'm going to show you how to do a power analysis. The way you would do the power analysis now is that you're going to do a certain number of simulations. So let's say 10,000, and I want to do a large number of simulations just because I can. and I'm going to compute the p-value. I'm going to generate simulated data each time, each of these 10,000 times. I'm going to fit a linear model to the that generate simulated data. I'm going to extract the p-value like I just showed you. I showed you how to extract the p-value. So I'm going to extract the p-value and save it in a vector, right? And then I'm going to check the proportions of times in those 10,000 cases that I had a p-value that was less than 0.05, and that is my statistical power, because that is the proportion of times that I rejected the null hypothesis correctly. Why correctly? Because the true value of the effect is 50 milliseconds, right? I had set that up. I had set up the simulation in this way that the null hypothesis was actually false. Alright, so now the question is, how do I do this simulation? So this is an exercise for you right now. So what you must do is you should pause the video and try to write this for loop yourself. Don't jump ahead to the next part of the presentation. Just stop the video and try to follow my instructions here and compute your power. Okay, so I'll continue now, but I'm hoping that you will stop at this point and try to do this for loop yourself. Here's the solution. The solution is that I'm going to create a vector for p-values, storing the p-values with nsim cells which are empty, and then for nsim simulations I'm going to generate between subjects simulated data. I'm going to fit a linear model to that and save it as an object M, and then I'm going to extract the p-value as I showed you earlier and put it into the p-vals vector in the ith cell. And then after the for loop is over, I'm going to check the mean number of times, so the proportion of times that these p-values are below 0.05, and I'm going to save print out that result by rounding it to 2 decimal places, and lo and behold, we get a similar answer of 0.06 to the one that we got at the very beginning of this lecture. Okay, so now we can also check whether the model can recover the true parameters under repeated sampling. This is an important check, because what this tells us is that the model, given the kind of assumptions that we have set up, for the generative process of the data. So whenever you fit a statistical model to some data, what you're implicitly doing is that you're asserting that you believe that the underlying generative process that produced that data from human beings can be modeled by the equation that you put in Elmer or whatever, right? So that's, you're defining a generative process. So what this simulating, checking whether the parameters can be recovered is an interesting way to check whether the model is valid, in the sense that can the model in principle recover the true parameters under repeated sampling. So what we're going to do is 10,000 times we will run the same thing that I just showed you. We're going to simulate data 10,000 times, fit a model to the simulated data each time, and each time we will extract all the parameters from the model. There are only 3. There's the intercept, slope, and the standard deviation. So what I've done is I've created a matrix called params, which contains 3 times the number of simulations in a 10,000 by 3 matrix. Okay, so in the first column of the matrix I'm going to stick in the intercept, the second column of the matrix I'm going to stick in the slope, and the third column of the matrix params I'm going to stick in the standard deviation. So that's what I've done here. In the ith row of the params matrix, the first 2 columns will be filled by the intercept and slope. That means the first column of the coefficients, right, from the summary output. And right, so you remember what I'm talking about here. So I showed you earlier here, right? So I've got a 2 by 4 matrix here. The first column is the coefficient. This is the coefficients. These are all the coefficients. The first column is this thing here, the intercept and slope. So I'm extracting that in this code here, right? So I've just extracted the first column, okay? And then the third column of the params matrix will be filled with the sigma value, the standard deviation, okay, from each of the simulations. So what I have is 10,000 estimates of the intercept, 10,000 estimates of the slope under repeated sampling, and 10,000 estimates of the standard deviation. Now I also know the true values of these numbers, right? 700, 750, no, sorry, 700, 25, and 300, right? So these are the numbers. So what I've done here is I've plotted the distribution of the intercepts under repeated sampling. I've plotted the distribution of the slopes under repeated sampling and of the sigma under repeated sampling, and the vertical lines that you're hopefully able to see here, these vertical lines are actually the true values. This is 725, this is 25, and this is 300, right? And what you can see is that the model, the distribution of the parameter estimates is centered bang around the true value. That means the model is able to nicely recover the true parameters, right? This is an interesting check, because what this tells us now is that the data generative process we have defined for the data we are analyzing, and of course we are analyzing simulated data, right? So what we are doing is we are generating simulated data because the simulated data expresses our belief about the underlying generative process. Okay, so what this parameter recovery process is telling us is that the model is able to recover these parameters under repeated sampling, and what that means is that it's a generally quite a reliable recovery. How can I say this better? That we can be generally confident that the underlying generative process that we've defined is a reasonable one. Okay, in this case, of course, it's a reasonable one because it's such a simple process, and we actually set up the simulated data ourselves, and then we analyze the simulated data using a known function. We know how the function, what the function was that generated the data, but later on when you look at more complicated cases with repeated measures data, the more abstract parameters, the random intercept standard deviations, the random slope standard deviations, the correlation between intercepts and slopes, you might think that your model is a reasonable one, but you may not be able to recover those parameters under repeated sampling. Okay, so I'll show you an example in a moment, and that shows you that the model, and that will show you that the model that you're trying to fit is too ambitious. So you should back off to a simpler model, because you can't even recover those parameters in principle, right? In the more complex cases. Example is coming up later on when we talk about within subjects designs. Okay, so I just said all this, that parameter recovery tells you the properties of your model under repeated sampling. This is something you can't do in real life, but with simulation you can certainly find out if your model will recover the parameters. Okay, all right, so now the next part of this lecture is about generating within subjects data. So I'm going to stop this recording now because this will be part 1. I don't want to make each of these lectures too long, because I've noticed that it's very difficult to upload the lectures to YouTube if they are too long. Okay, so this is part 1. I'm going to stop here. This was the between subjects data that we discussed. In the second part, I will discuss how to generate within subjects data.